My name is George Kokotinis and I'm a research engineer in Laboratory for Manufacturing Systems and Automation at the University of Patras in Greece. This is a training session for augmented reality-based tools designed to facilitate professionals in the manufacturing sector, including engineers and operators, to understand the potential of augmented reality technology within industrial settings. In the following course, you will listen about practical applications of AR technologies, demonstrating its utility in step-by-step instructions and efficient robot programming for both operator support and seamless human-robot collaboration.
Well, here are the main contents of today's training session. At the beginning, we will discuss about the augmented reality principles and fundamentals by presenting the main concepts and key aspects of AR applications for manufacturing. Then, we will talk about the AR applications for seamless human-robot interaction and operator support. We will present several human-robot collaborative scenarios and AR applications trying to enhance seamless human-robot interaction. Under this, we will also provide you with training on Unity application environment, focusing on developers to get them familiarized with the instructions provision for operator support. In the end, we will talk about the integration of AR technologies with robot programming functionalities and operator support by providing you again with training on how we can use AR tools for intuitive robot programming. So, let's start with what is augmented reality and how to use it for operator support. Augmented reality is an enhanced interactive version of a real-world environment achieved through digital visual elements, sounds, and other sensory stimuli, holographic technology. The hardware devices that we can use to have augmented reality can be monitors, optical projection systems such as projectors, handheld devices such as mobile phones or tablets, head-mounted displays, eyeglasses, and contact lenses. The main components of augmented reality solutions are the following 5. The first one is the AR software, meaning all the tools and applications used to access augmented reality. Then, we need the processing unit to provide the power to the AR technologies in order to work. After that, we need to develop artificial intelligence algorithms for our augmented reality solutions in order to allow voice prompts and processing information and data for the AR application. Users need also a lens or image platform in order to view all the content and images. In the end, sensors are very important for the AR systems in order to digest data about their environment to align the real and the digital world. There are 2 types of augmented reality. The first one is a market-based AR, and the second one is marketless. As for the first one, it is created using image recognition to identify the programmed object. What we need for this type of AR is to place objects in view as points of reference that can help the AR device determine the position and orientation of the camera. Then, a mathematical determination is needed for the pose and the placement of the AR image in the right spot. As for the marketless AR, there is no point in which the device will focus on. Now, the device must recognize items as they appear in view. A recognition algorithm is needed to look for colors, patterns, and similar features to determine what the object is. Then, using a time accelerometer, GPS, and compass information, it will orient itself and use a camera to overlay an image of whatever the user likes within the real-world surroundings. Some of the benefits that augmented reality applications can provide are the improved user experience thanks to the visualization of the trajectory of the upcoming robot, the reduction of both training needs and time for robot programming, the increase of the operator and common among manufacturing teams, the creation of awareness, support of the operators when human-robot interaction is needed, increased responsiveness to production deviations such as material shortages or something else, and the assurance of data and information synchronization among the different operators and workstation actors such as robots or machines, etc. Augmented reality can also provide benefits towards operator support in manufacturing, focusing mainly on cognitive ergonomics. Cognitive ergonomics aims to improve the matching of cognitive requirements to the operator's cognitive capabilities. They focus on mental interactions of the operators with the manufacturing system, and cognitive processes such as interpretation of data, situational awareness, decision-making, learning the procedures and remembering them, or being provided with instructions. By using such operator support tools, so augmented reality, we can achieve the reduction of the occurrence of safety accidents, reduction of human errors, reduction of turnover and costs for hiring and retraining personnel, and of course reduction of operator burnout. Apart from the benefits that augmented reality tools can provide for operator support in manufacturing, we can also facilitate human-robot interaction. Here you can see some examples of optical projection systems and projectors. In the left figure you can see projectors that are integrated in a robotic cell that can show to human operators the safety zones as well as the areas that the robot is operating. As for the second figure, in the right, you can see projectors that show to the operator step-by-step instructions for process execution and some visual cues to guide the rotation. Previous studies have also been conducted focusing on the integration of augmented reality-based tools to achieve human-robot interaction between human operators and mobile robot. LMS in such studies mainly focused on: first, robot programming, by meaning that the operator can show to the mobile robot what to do through the augmented reality tools. Second, assembly guidance, by meaning of detailed instructions to the operator for the assembly process. Third, safety awareness, by meaning of visualizing safety zones or cues about the robot operation, and fourth, resilience. Here you can see some other examples of integrating augmented reality tools for human-robot interaction and operator support. As you can see in the top figures, AR-based tools have been used for the introduction of robot resources and the visualization of robot-related information such as robot trajectory or working areas, etc. We can achieve an intuitive and safe human-robot interaction by visualizing safety zones to the operators. They also provide benefits for operator support by visualizing process-related information such as instructions or times for work, etc. AR tools help for physical object tracking or dynamic distractions during training, as well as they can represent assembly processes through virtual objects. This training session takes place under PeneloPe Project, and one of the main aspects of PeneloPe is the development and integration of human-centric tools that can support the operators during the assembly of large-scale parts. LMS works mainly on the bus and coach sector, which focuses on the assembly of large sidewall panels. This assembly of sidewall panels includes numerous processes such as the manipulation of the entire panel, the assembly of big parts on the panel, and the quality inspection and repairing of the entire panel. For all these processes, multiple operators are used, as well as many robots have been integrated of different types. For all these reasons, AR-based tools can be very helpful in all these processes in order to support operators during process execution in the software, as well as to achieve intuitive human-robot interaction. More specifically, under PeneloPe Project, LMS created an AR-based application that can be used by multiple operators to work under the same process at the same time. This application increases situational awareness by visualizing both robot-related data, such as robot trajectory, safety mode, or safety zones, as well as process-related information, such as process defects or process constraints, or the robot task completion time, etc. In addition, this application enables operators to work in teams and having common situational awareness, as well as it enables the visualization of dynamic task feeds, as you can see here in the video, in order for all the operators to see the same events in the process. Moreover, it achieves real-time continuous and personalized updates of the operator's view, based on the shop floor conditions and actions. For example, here you can see an operator trying to solve a defect found in the glue line, and after solving it, the defect disappears from both the operators, as well as from the task list dynamically. In the end and under this concept, LMS also created a digital twin of the process that can be used for remote supervising of the process by an engineer. As for the operator support in industrial environments, humans usually have to execute complex tasks and many times difficult to remember all the exact steps. In this view, operators need tools that can help them by providing step-by-step instructions and material during process execution. Such a tool can be augmented reality. Here, you will see a short training session on how non-expert developers can create panels for AR-based applications to provide process instructions and visual material like videos or photos. According to our case, we will show you an example of facilitating operators on properly wearing and regulating Mate XT exoskeleton of Como, since this can be considered a complex procedure with several steps and regulations that need to take place. The first thing you need to do to create an AR application is to download and install Unity. For this, go to the Unity Hub, then go to Installs, and install the Unity 2090.4.17f1 version. After installing this version, create and open a new project, and the Unity environment will open. In this environment, you can see the scene of your application on the left side and, below that, all the files you are using in your project. In the middle, you will see the hierarchy of your project, which includes all the game objects you use, such as panels, buttons, etc. On the right side, you'll see the inspector, containing all the functions and scripts you created for each game object in the hierarchy. It's important to note that, since we are creating this application for AR-based tools, in our case using Microsoft HoloLens 2 AR glasses, you need to import the Mixed Reality Toolkit into your project. The toolkit includes essential functions, templates, panels, and buttons for your project. Once done, we can proceed with visualizing our application. The first step is to create the panels we will use. To create a panel, right-click in the hierarchy, go to UI and then select Panel. This will create a canvas and, beneath it, the panel. Since the application is for AR glasses, you need to convert this canvas to MRTK canvas to be used of Microsoft HoloLens 2. Then, add the Near Interaction Touchable Unity UI function from the inspector to this canvas. After that, your panel will be ready. In our case, we created two panels, the main menu and the wearing instructions menu. The main menu acts as a navigation panel, allowing users to access other panels. This menu contains buttons that, when pressed, lead to other panels. On the other side, the wearing instructions menu is our important panel, which is the one that will provide step-by-step instructions to the user in both text and visual material. Well, now, it is time to explain a little bit about the structure of the panels that we have created. We split each menu into two sections, the title bar and the content backplate. The title bar is consistent across all panels, while the content backplate varies. For the title bar, we include a title, where in our case we named this panel Main Menu. This is a Text Mesh Pro object created from the UI option. We have also some buttons, such as a button to close the application, and then logos for visualization where we used the LMS and Penelope logos. The content backplate is the most important part of each panel. In the first canvas, you can change or add material to adjust colors as needed. For example, you can change the color to gray. The content backplate contains all the buttons and content for each panel. In our case, we created a Wearing Instructions button that leads to the second panel, which provides instructions and videos for the operator. To create a button, the Mixed Reality Toolkit provides template buttons. After importing MRTK, you can find a button prefab, drag it into your hierarchy, and adjust its position or scale. You can then modify the title or icon of the button and assign a function to it. For example, you can change the title by selecting the text field in the Text Mesh Pro object or the icon by selecting Icon field in the Wearing Instructions button object. You can add the desirable function in the Basic Events and On Clinic field of the Wearing Instructions button. Now, let's discuss the second and most important panel for today's training, the Instructions panel. Like the first panel, it has a title bar with the title and logos. It also includes a home button that refreshes the page and takes you back to the main menu. The content backplate contains buttons such as Start Tutorial, Next Instruction, Previous Instruction, etc. Additionally, there are two other fields: the narrator box, which provides text instructions to the operator, and a section for videos and images. For the narrator box, we created two backgrounds to create space for our text and added a Text Mesh Pro object for displaying the instructions. In order to add instructions in text, we use the dialog object from the hierarchy, which is a Text Mesh Pro object created by right-clicking and selecting UI and Text Mesh Pro. To add videos, you can import a video into your project, create a video player, and assign the video to play on a specific panel. Once all the panels and buttons are created, it's time to write the scripts and assign functions to the buttons. Go to your files, create a folder for scripts, and then create a script. After naming the script, it will open in Visual Studio. The first script we used is a dialog class, which defines the input, a list of sentences and videos used for each process step. The second, more important script is the dialog manager, where we define variables and functions for the application. These functions are then assigned to the corresponding buttons on the panel. For instance, the Start Dialog function clears previous instructions and videos and queues up the next set for display. The Start Dialog function is going to be assigned in the Start button we created in the hierarchy under the Wearing Instructions menu. The Restart dialog is almost the same function with the previous one, but now the user can press the corresponding Restart button anytime he wants, and by this he starts again the instructions provision from the beginning. Another important function is Display Next Sentence, which is linked to the Next button and moves the operator to the next instruction. This function also hides unnecessary buttons, like the Previous button when on the first instruction or the Next button when on the last instruction. We also created a Display Previous Sentence function for moving to the previous instruction. The final function displays the instructions text letter by letter, providing a time gap between each letter to facilitate reading. Additionally, we created a function to end the tutorial and return to the main menu. After writing these functions, they need to be assigned to the corresponding buttons. For example, the Start button is linked to the Start Dialog function. This process is repeated for all buttons. For this reason, we created our third and last script, which we'll use to trigger all the created functions to the corresponding buttons, about starting and restarting the dialog, or go to the previous and the next instruction. To assign functions, go to the button collection, find the relevant button, and assign the function in the On-Click Events section. Now that the functions are assigned, the application is ready. The only remaining step is to add the instructions and videos for visualization. This is done by using the dialog trigger function and filling the public variables for sentences and videos. For example, we added 15 instructions, sourced from manuals provided by Comau, to instruct the operator on wearing and adjusting the exoskeleton. We also added relevant videos and images for visual reference. All these videos and images have been stored in a folder created in the project's files named Exoskeleton. Then, in order to assign and visualize them, we just need to drag and drop them in the corresponding fields of the narrator box. Once everything is set, you can start the application. From the main menu, pressing the first button takes you to the Wear and Regulations panel, where the tutorial begins. Instructions are displayed letter by letter, accompanied by a video. You can navigate through the instructions using the Next and Previous buttons, or restart the tutorial if needed. At the end, the Next button is replaced by an End button, which takes you back to the main menu. This is our application. I hope this training helps you understand how to create panels and provide text and video instructions to the operator. In addition, under PeneloPe Project, LMS enriched the developed AR application focusing on intuitive and interactive robot toolpath programming. Some of the main functionalities of application under this scope is the verification of toolpaths generated, the intuitive generation of robot waypoints by creating some spheres in the AR environment, as well as the direct robot end effector positioning by moving the entire hologram of the robot. The main benefits of this application is that 1. No expertise in robot programming is needed. 2. The programming of robot motion is user-friendly and it is enabled using virtual objects and sliders. 3. More than one tool for robot programming in accordance with the user preference can be used, such as points or robot hologram, etc. 4. It achieves reduction of robot programming time, and 5. The perception of kinematics of the robot is achieved without running the real robot, enhancing in this way the user experience. In this slide, you can see a short demonstration of the AR-based application that LMS created, focusing on intuitive and interactive robot toolpath programming. Engineers theoag this application can generate new waypoints intuitively in a matter of seconds, where these waypoints, as you can see in the video, have the form of spheres, these yellow ones, that the operator can place them in the area wherever he wants. Then, after placing all these waypoints, he starts to execute the process and the plan path, so at the beginning he can see the robot hologram to visualize the programmed path, and then the real robot to execute it. In addition, engineers can change some settings, such as the robot speed or the curvature of the path, and after these updates, you can see again the new robot path that has been programmed. No expertise is needed to use this tool, expertise in robot programming, and the engineers can have a direct visualization of the toolpath waypoints in the 3D space. In addition, as you can see here in the video, engineers can position the entire end effector of the robot whenever they want, so he can make a first movement in order to pick up an object such as the dummy window that we have placed, and then a sequence of movements in order to place it or approach it to the correct position of the sidewall panel for installation, as you can see in the video. Again, here both the hologram and the real robot execute the path. In the end, after programming 2 or more movements, or 2 or more paths, as we name them, the engineer can see the entire process simulated, as you can see here. So, you can see the first movement of picking up the end effector, then the robot that goes to the placing position, and in the end, if this path is the desired one, he can store it and teach the robot to execute it. Here, you can see a training session of how the AR-based application shown in the previous slide can work in real time, and how an operator, or engineer, can program a high-payload robot, such as the one that we use under PeneloPe. The first step of this training session is to explain a little bit about the application that LMS created for AR glasses, focusing on the high-payload robot programming. This is the main menu of our application, and as you can see, it is based on the instructions provided in the previous video of this training material on how to create a menu for an application in Unity. Here, you can see the functions we have created for our application, as well as a settings button. When the user presses it, they can change options related to the trajectory view, see the robot hologram, trajectory points, etc., adjust transparency, or view the robot's safety zones. They can also calibrate the robot through this menu. We have placed a QR code on the real robot, and when we press this button and scan the QR code, we can place the hologram on the real robot and match the pose with the actual robot. After that, we have 3 choices or menus for robot programming. Let's first talk about the bottom 2. The first one is robot path pitching, where we generate the waypoints for the robot. By pressing this button, you can see spheres are created, which we can then place in the robot's working area. After that, we can simulate the robot's path, and once completed, execute the path. As you can see, after pressing Execute Path, the robot moves to the position we set. We can also delete each waypoint we generated and create new ones wherever we prefer. The second tool our application offers is End Effector Positioning, where you can place the end effector wherever the user prefers. As you can see, we have a separate hologram for the end effector. For example, we place the robot in a position slightly higher than before, and again we can simulate and execute the path. When we execute it, the robot follows the optimized path that the planner generated, reaching the final position. Our last tool allows us to create an entire robot task sequence by pressing this button. Here, you can see the robot operation library, where we can add, for example, 2 operations. Pick and place. We can see this operation here, and then configure the task sequence. Pressing the next panel, we see the 2 operations again, and we have selected the first one, pick. For this operation, we must select the part we want to use, for example, the window, and define the robot path to execute this operation. We can use either of the previous 2 functions. Here, we use the robot path with the spheres, place a sphere below the robot, execute it, and the robot moves as demonstrated. We save this path and move on to the next operation, place. Again, we select the part, the window in this case, and define the path for this task. We place a sphere a bit lower, execute, and now we have two operations in the task sequence. We save again, and in the end, we can save the entire task, simulate both operations, execute them, and export them to a file. When exported, you can see the robot executing both operations. The first one was up, and the second one was down, just as we placed them. This is the application we created, and now we can see how it works with the real robot. In live action, the first step the user must take is to calibrate the robot. As you can see on the screen, the user approaches the QR code placed on the back of the robot, presses the calibration button, and an X, Y, Z axis is created, allowing the entire robot to be calibrated. You can now see the hologram on the real robot. Next, the user positions the end effector to grasp the window. By pressing the button and using a hand gesture, a sphere is created, and the user tries to approach the window. The end effector is set to the first position, but the user sees it needs a slight modification, so they adjust the sphere downward to position the suction cups on the window. After executing, the suction cups successfully grasp the window. The user then begins to create a task sequence by adding operations. The first is the picking operation, followed by the move arm operation to adjust the robot's position, and finally, the placing operation. After adding these to the task sequence, the user configures each operation by selecting the part, in this case, the window. For the picking operation, the user positions the end effector higher to lift the window. After executing, the robot begins to lift. The user notices that the frame in the AR glasses view is slightly misaligned, adjusts it, and proceeds to configure the second operation, the move arm. They rotate the end effector 90 degrees to approach the window on the panel side. After turning it 90 degrees, they execute again, and the robot moves to the new position. It's preferable for the robot to make small adjustments during operations rather than moving directly from the initial position to the final one, as this helps avoid collisions. More operations are added for small modifications. The user then moves on to the next operation, another move arm function, to rotate the window into the correct orientation for final assembly. The end effector is turned 90 degrees again, and you can see the adjustment on the hologram behind the user. After setting it, the path is executed, and the window turns 90 degrees to its final orientation. The user saves this operation path, and the final one is the placing operation. Although we won't see the full assembly of the window, the user positions it near the sidewall panel. The user notices they can approach it a little more, modifies the final path, and positions the robot closer to the window frame. After executing, the robot moves to this final position. Now that the user has created all the operations and the full task sequence, they save the entire task. They go to the final menu, select Save Task, and export the task sequence to a JSON file. You can see the robot executing all the paths and operations created. The first position for picking, the second move arm operation at 90 degrees, followed by another rotation at 90 degrees, and finally, approaching the window for placement. In this way, the user has programmed the entire task sequence for picking and assembling the window. After programming and teaching the robot this task, the user may make further adjustments, such as moving the end effectors even closer to the sidewall panel for final assembly. Thank you for attending this training session for AR-based tools and applications, focusing on human-robot interaction and operator support. I hope this session was very helpful for all the non-expert users and developers of AR tools, as well as for operators, engineers of industrial sectors. Please do not hesitate to contact me in my mail in case of any comments or questions you may have. Thank you.